Have you ever stood outside on a clear night, looking up at the stars, and felt that strange mix of awe and unease, that quiet hum of curiosity, wondering just how far it all goes, and whether the universe has an edge, or if it stretches on forever? It's a question that's haunted humanity for thousands of years, whispered in ancient myths, carved into temples, and now tested by the most advanced telescopes and equations we've ever created. Because here's the wild part, we still don't know for sure. The shape of the universe isn't just some abstract idea. It's the ultimate puzzle, one that could rewrite everything we think we understand about reality itself. Picture this: space might not be the endless, flat expanse we assume. What if it curves gently, like the surface of a balloon, or twists in ways our brains can't even visualize? Some theories suggest the cosmos could loop back on itself, travel far enough in one direction, and you'd end up right where you started. Others argue it's infinite but warped, a vast cosmic fabric pinched and folded by gravity. And then there's the haunting possibility that our entire universe is just one bubble in an endless froth of parallel realities. These aren't science fiction. These are real, testable ideas, born from the equations of Einstein and the observations of satellites mapping the faint afterglow of the Big Bang. So how do we begin to unravel a mystery this colossal? By stitching together clues from across time and space, ancient astronomers charted the heavens with nothing but their eyes and stone tools. Today, we peer deeper into the void with machines that catch echoes from the dawn of time. Every measurement, every flicker of distant light is a piece of the puzzle, and what we're finding challenges everything we thought we knew. This journey isn't just about science, it's about stepping to the edge of human understanding and staring into the unknown. By the end, you won't just see the night sky differently, you'll feel it. The universe isn't just out there, it's a story we're all part of, and its shape. Well, that's where things get truly extraordinary. The night sky has always been humanity's first classroom. Thousands of years ago, when civilizations like the Greeks, Mayans, and Babylonians looked upward, they didn't just see stars, they saw a cosmic riddle waiting to be solved. Aristotle imagined the universe as a series of perfect, nested spheres, with Earth at the center and the heavens rotating around us in harmonious, eternal motion. It was a comforting idea, finite, orderly, and built around us, but not everyone agreed. The Roman poet Lucretius dared to suggest something radical: that space had no end, stretching outward without limit. His words, written over 2,000 years ago, still echo in modern debates about the universe's true nature. These early thinkers didn't have telescopes or satellites. They relied on observation, philosophy, and sheer imagination. The Mayans tracked celestial movements with astonishing precision, aligning their pyramids to the stars, while Greek astronomers like Ptolemy mapped the heavens with geometric precision. Their models were often wrong, but the questions they asked, does the universe have boundaries? Is space curved or flat? Are the same ones scientists grapple with today. It's humbling to realize we're part of a chain of curiosity stretching back millennia. What's remarkable is how close some of these ancient ideas came to modern theories. The concept of an infinite universe wasn't just philosophical speculation, it was a bold leap into the unknown. And while Aristotle's crystalline spheres may sound quaint now, his insistence on a structured, knowable cosmos laid the groundwork for the scientific method. These early cosmologies weren't just myths. They were the first steps in a journey that would eventually lead us to relativity, quantum physics, and the mind-bending idea that the universe might not be what it seems. The night sky hasn't changed, but our understanding of it has, and that transformation began with those first stargazers who dared to ask, what lies beyond? Einstein didn't just change how we think about gravity, he shattered our entire picture of reality. Before him, space was seen as a rigid stage, an unchanging backdrop where planets and stars moved like actors following Newton's script. But Einstein's general relativity rewrote the play. He revealed that space and time aren't just a stage, they're actors too, bending, stretching, and twisting in response to the mass and energy within them. Imagine placing a bowling ball on a trampoline. The way it warps the fabric beneath it is exactly how planets and stars distort spacetime itself. This wasn't just poetic imagery. It was a mathematical revolution, one that redefined the very shape of the cosmos. His equations suggested something even stranger. The universe might be finite but have no edge. Think of the surface of a balloon. As you blow it up, every point on that surface moves away from every other point, just like galaxies drifting apart in our expanding universe. But if you could walk in one direction forever on that balloon, you'd never hit a wall. You'd just loop back to where you started. That's the mind-bending idea of a closed universe, one where space curves back on itself in higher dimensions we can't see. Einstein's math allowed for other possibilities too, an infinite, flat universe or even a hyperbolic one, warped like a saddle. Suddenly, the question of the universe's shape wasn't philosophy, it was physics, something we could test. And test it we did. In 1919, during a solar eclipse, astronomers confirmed one of relativity's wildest predictions, starlight bending around the sun. It was the first hard evidence that space itself could curve. Decades later, satellites like Cobe and Planck mapped the faint glow of the Big Bang's afterglow, searching for tiny temperature variations that could reveal whether spacetime is flat, closed, or open. The results, they're still shaking the foundations of cosmology. The latest data suggests the universe is astonishingly close to flat, but with a twist. There's a nagging discrepancy, a cosmic tension that hints at something deeper we're missing. Einstein gave us the tools to ask these questions, but the answers keep surprising us. What's incredible is how much of this hinges on a single number, the density of the universe, too much matter and energy, and spacetime curves back on itself. Too little, and it stretches outward forever. Right now, the numbers suggest a Goldilocks scenario balanced on a knife's edge between collapse and eternal expansion. But here's the catch. We've only accounted for about 5% of the universe's total content. The rest, dark matter and dark energy, mysterious forces that warp spacetime in ways we're still struggling to understand. Einstein's equations pointed us toward these mysteries, but solving them might require another revolution, one as profound as his own. This is the legacy of relativity. It didn't just give us better equations, it gave us a new lens to see the universe, one where geometry isn't just about shapes, but about the fate of everything. And that's the thrilling part. We're still peering through that lens, still deciphering what the cosmos is trying to tell us. Every measurement, every observation is another stitch in the fabric of understanding. And somewhere in those equations, hidden in the curvature of spacetime, might lie the answer to the ultimate question: what shape is our universe really? The Big Bang didn't just light the fuse for the universe's expansion, it left behind a cosmic blueprint, a hidden code etched into the fabric of space itself. To crack it, scientists turn to the oldest light we can see, the cosmic microwave background. This faint glow, lingering from just 380,000 years after the Big Bang, is more than a relic. It's a snapshot of the infant universe, and within its subtle patterns lies the secret to spacetime's shape. Picture a vast, quiet ocean after a storm. The ripples on its surface tell you about the winds that shaped it. In the same way, those tiny temperature variations in the cosmic microwave background, fluctuations no larger than 100,000th of a degree, reveal how space itself might curve. For decades, satellites like WMAP and Planck have mapped these ripples with breathtaking precision, searching for clues in the universe's first light. The results hinge on a deceptively simple question: do parallel lines stay parallel forever, or do they eventually drift apart or converge? In a flat universe, they'd hold their course indefinitely, like lasers fired across an endless plane. But if space has positive curvature like the surface of a sphere, those lines would slowly bend toward each other, just as lines of longitude meet at the poles. A negatively curved universe, warped like a saddle, would send them veering apart. The cosmic microwave background acts as a cosmic ruler, letting us measure which scenario fits reality. Here's where things get fascinating. The latest data suggests the universe is remarkably close to flat, but not perfectly so. It's as if space is teetering on the edge between curvature types, balanced by some unseen hand. That near flatness isn't a coincidence, it's a clue to the universe's explosive beginnings. During the Big Bang, a fleeting moment called inflation stretched space so rapidly that any initial curvature was smoothed out like wrinkles in a pulled sheet. Yet the fact that we don't measure perfect flatness leaves room for tantalizing possibilities. Could there be larger-scale curvatures too subtle for our instruments to detect? Or does the slight deviation hint at something deeper, like the gravitational fingerprints of other universes beyond our own? The implications are staggering. A flat or negatively curved universe suggests infinity, a cosmos without end where space stretches forever into darkness. But a positively curved one, even slightly, would mean our universe is finite, looping back on itself in dimensions we can't perceive. Imagine sailing across what you think is an endless ocean, only to realize you've been circling a globe the whole time. That's the paradox of cosmic geometry. The universe's shape isn't just about space, it's about fate. A closed universe might eventually collapse in a big crunch, while an open one could rip itself apart in eternal expansion. Right now, the evidence leans toward flatness, but the story isn't over. Every new observation, from gravitational waves to dark matter's elusive pull, adds another piece to the puzzle, and perhaps the most humbling thought of all. We're not just mapping the universe's shape, we're tracing the edges of our own understanding, pushing deeper into the unknown with every flicker of ancient light. Right now, the leading theory about our universe's shape is as straightforward as it is staggering. Space might be perfectly flat, not just approximately flat, but so precisely balanced that if you could draw two parallel lines across the cosmos, they'd never touch, not even over billions of light years. In this scenario, the angles of a triangle would always add up to 180 degrees, just like in a high school geometry textbook. This isn't just a hunch, it's backed by some of the most precise measurements ever taken, from missions like Planck, which scrutinized the cosmic microwave background down to a millionth of a degree. The data is clear. The universe shows no detectable curvature, at least within the limits of our instruments. But here's the catch. A flat universe isn't just a neutral fact, it's a cosmic tightrope act. For spacetime to lack any curvature, the density of matter and energy must be exquisitely balanced, a condition cosmologists call the critical density. Too much mass and gravity would bend space inward like a sphere, too little, and it would warp outward like a saddle. Instead, we find ourselves in a universe that's balanced on a razor's edge, with the scales tipped by less than 1%. This precision is so improbable that it begs the question, why? How did the universe land on this exact equilibrium, as if fine-tuned by some unseen hand? Some theorists turn to the multiverse for answers. If our cosmos is just one bubble in an infinite froth of universes, each with different physical laws, then statistically, a few would inevitably land on the right conditions for flatness, and we'd find ourselves in one of those lucky few. Others propose even wilder ideas like the holographic principle, which suggests our three-dimensional universe might be a projection from a two-dimensional surface at its edge, a cosmic illusion that naturally enforces flatness. These aren't just thought experiments, they're serious attempts to explain why the numbers line up so perfectly, and they hint at a reality far stranger than we've imagined. Yet even the flat universe theory has its cracks. For one, it implies infinity, an endless expanse of space with no boundary, no edge, and no center. That's a concept our brains struggle to grasp. An infinite universe means there could be an exact copy of you somewhere out there, reading an identical script in a galaxy so distant its light will never reach us. It also raises thorny questions about the nature of dark energy, the mysterious force accelerating the universe's expansion. If space is truly infinite, why does dark energy's influence seem so uniform, as if it's woven into the fabric of nothingness itself? The flat universe model is our best guess, but it's far from the final answer. Later, we'll dive into the alternatives: closed universes that curve back on themselves, open ones that stretch into fractal infinity, and even theories that suggest our entire cosmos is a rotating, twisting entity shaped by forces we've yet to name. For now, the flatness of space stands as both a triumph of measurement and a profound mystery, a reminder that even the simplest geometry can hold the universe's deepest secrets. A spherical universe isn't just a geometric curiosity, it's a cosmic hall of mirrors, where every straight line eventually circles back on itself. Imagine setting off in a spaceship, flying what you think is a straight path through the void, only to find yourself returning to your starting point from the opposite direction. In this scenario, the universe isn't infinite, it's a vast, four-dimensional sphere, curved so subtly that we'd never perceive the bend in our daily lives. Light itself would follow this curvature, tracing great cosmic arcs across spacetime. It's the ultimate closed loop, a universe with no boundaries yet finite in size, like the surface of a planet expanded to unimaginable scales. This idea isn't just poetic, it's mathematically elegant. A positively curved universe would resolve one of cosmology's oldest paradoxes: how something could be both boundless and limited. No edges to stumble into, no mysterious outside to explain. Everything simply folds back into itself, a self-contained cosmic egg. Early 20th century thinkers loved this model for its tidiness, and even Einstein flirted with the idea, proposing a static, spherical universe before Hubble's discovery of expansion forced him to reconsider. Yet for all its appeal, the spherical universe faces stiff challenges from modern observations. Distant supernovae, used as cosmic yardsticks, suggest the universe's expansion is accelerating behavior that's hard to square with a closed, finite shape. Galaxy surveys, too, show patterns of large-scale structure that align better with flat or hyperbolic geometries. But here's the twist: there are lingering anomalies. The cosmic microwave background reveals slight discrepancies, regions where temperature fluctuations don't quite match predictions for a perfectly flat universe. Some researchers argue these could be whispers of curvature, subtle enough to evade detection in most measurements, but hinting that space might curve on scales larger than we've yet probed. Then there's the philosophical weight of a closed cosmos. A spherical universe would eventually stop expanding and collapse inward in a big crunch, a mirror image of the Big Bang. Time itself would have a bookend, a final chapter written in the physics of collapse. It's a dramatic vision, one that appeals to our love of symmetry. But until we find definitive proof, perhaps in the faint gravitational waves from the universe's infancy, or in deeper mappings of the cosmic web, the spherical model remains a beautiful what if, a reminder that the cosmos might still surprise us. Now let's flip the curvature the other way. What if space isn't flat or spherical but stretched like a saddle, warped by negative curvature? This is the hyperbolic universe where parallel lines don't just diverge, they explode apart, racing into the void like runners on an ever-expanding track. Here, geometry itself becomes surreal. Triangles bulge inward, their angles summing to less than 180 degrees. Circles grow exponentially larger as their radii increase, their circumferences outpacing the familiar 2πr rule. It's a universe where nothing behaves as expected, a hall of mirrors far stranger than the gentle curves of a spherical cosmos. The hyperbolic model isn't just mathematical fantasy, it's a real possibility that emerges from Einstein's equations. If the universe's density falls below the critical threshold, gravity loses its grip and spacetime sags outward like a hammock weighted with too few stones. Distant galaxies would appear distorted, their light stretched and smeared by the extreme curvature. Yet oddly, this isn't what we see. Observations suggest the universe is too close to flat for hyperbolic geometry to fit neatly. But just as with the spherical model, there's room for doubt. Some theories propose that dark energy's influence could mimic aspects of negative curvature, or that local measurements might mask a larger, more complex shape. What makes the hyperbolic universe so compelling isn't just its geometry, it's the implications. In this scenario, space isn't just infinite, it's exponentially infinite, with volumes doubling and redoubling as you venture outward. The sheer scale defies comprehension. A traveler here would find the universe growing stranger with every light year, distances stretching like taffy in ways that make navigation impossible. It's a cosmos without center or edge, where even the laws of physics might warp over vast distances. Yet for all its grandeur, the hyperbolic model remains on the fringe, not because it's impossible, but because the evidence so far resists it. The cosmic microwave background's patterns, the distribution of galaxies, the behavior of distant supernova, all lean toward flatness, but cosmology has taught us humility. Every time we've assumed we've pinned down the universe's shape, new data has forced us to rethink. Whether spherical, hyperbolic, or something stranger still, the true geometry of spacetime might be waiting just beyond our current reach, hidden in the next generation of telescopes or the faint echoes of gravitational waves. The search isn't just about maps and measurements, it's about understanding the stage on which all existence unfolds. A saddle-shaped universe isn't just a mathematician's daydream, it's a realm where the rules of geometry break wide open. Picture riding a horse across an endless, warped landscape where every horizon curves away from you. In this hyperbolic cosmos, space doesn't just expand, it stretches exponentially, like taffy pulled in all directions at once. Here, two parallel laser beams fired into the void wouldn't just drift apart over time, they'd flee from each other, as if repelled by an invisible force. Triangles drawn between stars would defy Euclid, their angles adding up to less than 180 degrees, while circles would grow so rapidly that their circumferences would outpace their radii. This isn't abstract theory. It's a direct consequence of Einstein's equations when the universe's density falls below a critical threshold, leaving spacetime too light to curve inward. Yet for all its mathematical elegance, the hyperbolic model faces a glaring obstacle: the eerie uniformity of the cosmic microwave background, those faint temperature fluctuations we've mapped so precisely. They're almost too smooth, too balanced to align with the chaotic sprawl of negative curvature. A truly saddle-shaped universe would distort the afterglow of the Big Bang in ways we don't observe, stretching some regions into smears while compressing others into sharp peaks. But here's where the plot thickens. Some theorists propose that extra dimensions, curled up at scales far smaller than an atom, could warp spacetime in localized pockets, creating hyperbolic regions hidden within a larger, flatter cosmos. It's like finding a crumpled sheet of paper in an otherwise tidy room, a cosmic anomaly that hints at deeper layers of reality. This ties into one of the most tantalizing ideas in modern physics: topology, the study of shapes and their connectivity. Imagine the universe not just as a smooth fabric, but as a twisted Möbius strip or a knotted pretzel in higher dimensions. Topology could allow a hyperbolic universe to fold in on itself in ways that evade our telescopes, disguising its true shape. String theorists take this further, suggesting that the extra dimensions required by their models might generate hyperbolic curves too subtle for current instruments to detect. It's a reminder that the universe's geometry isn't just about curvature. It's about how that curvature connects, loops, and tangles across scales we're only beginning to probe. So why does this matter? Because the shape of spacetime isn't just a cosmic curiosity, it's a roadmap to the universe's fate. A hyperbolic universe would expand forever, accelerating into a cold, thin void where distant galaxies vanish over the horizon of perception. But if patches of negative curvature lurk in hidden dimensions, or if topology weaves space into unexpected forms, our cosmic endpoint might be stranger than we've dared to imagine. The saddle-shaped cosmos remains an underdog in the race to explain reality, but its very possibility stretches our understanding of what the universe could be and where it might ultimately take us. What if our universe isn't just an endless expanse, but a cosmic donut? Not the sugary kind, of course, but a shape mathematicians call a torus, where space loops back on itself in hidden dimensions. Imagine playing an old-school arcade game where your spaceship disappears off the right side of the screen only to reappear on the left. Now scale that up to the entire cosmos. Fly far enough in one direction, and you might hypothetically return to your starting point from the opposite side, like an ant crawling around the surface of a donut without ever hitting an edge. This isn't science fiction, it's topology, the study of how shapes connect, and it could rewrite our understanding of the universe's true size. The idea hinges on a subtle distinction. Flatness doesn't necessarily mean infinite. A piece of paper is flat, but roll it into a cylinder and it becomes finite yet edgeless. Twist that cylinder into a donut shape and you've got a torus, a surface where parallel lines stay parallel, yet space is mysteriously finite. Apply this to the cosmos and suddenly, even a universe without curvature could be smaller than we think, folded into a higher dimensional structure we can't see. The math checks out, and some models even suggest this could explain odd symmetries in the cosmic microwave background, like matching temperature patterns on opposite sides of the sky, as if space were a room with mirrors on every wall. But here's the catch. Proving this would require spotting identical galaxy clusters or radiation patterns repeating across vast distances, like finding the same mountain range on opposite sides of an alien globe. So far, no such duplicates have been confirmed. The Planck satellite's painstaking maps of the early universe show hints of potential matching regions, but the signal is faint, like hearing an echo so distant you're not sure it's real. Critics argue these patterns could just be cosmic coincidence, while optimists point out we've only surveyed a fraction of the observable universe. The real smoking gun might lie in gravitational waves, ripples in spacetime that could carry imprints of the universe's topology as they travel through its hidden folds. A toroidal universe wouldn't just be a geometric curiosity, it would force us to rethink everything from the Big Bang's aftermath to the nature of dark energy. If space loops back on itself, the expansion we observe might be more like inflating a rubber donut than stretching an infinite sheet. Even time could behave differently in such a cosmos, with particles potentially orbiting the universe's hidden dimensions like cars on a racetrack. And then there's the philosophical kicker. A finite universe means everything, including you, could exist in multiple places at once if you traveled far enough along the cosmic loop. The wildest part, a donut-shaped universe, is just one topological possibility. Space could be a kaleidoscope of twisted ribbons, a 12-sided dodecahedron where opposite faces seamlessly connect, or even a Klein bottle, a shape so bizarre it has no inside or outside. Each model predicts unique patterns in the cosmic microwave background, like fingerprints waiting to be decoded. Until we gather more evidence, the universe's topology remains a tantalizing what if, a reminder that reality might be far stranger than the infinity we've always imagined. Now, let's talk about the elephant in the cosmos, dark energy. This mysterious force isn't just accelerating the universe's expansion, it's stretching the very fabric of spacetime, warping our geometry in ways we're only beginning to grasp. If the universe is a donut, dark energy might be the unseen hand twisting its shape, pulling it taut or crumpling it into new forms over billions of years. The connection between topology and dark energy isn't just theoretical. It could hold the key to understanding whether our universe is infinite, finite, or something beyond our current math. Dark energy isn't just some abstract entry in a physicist's notebook. It's the universe's most enigmatic architect, silently reshaping reality itself. Picture a runaway train hurtling faster with each passing second, its acceleration defying every expectation. That's precisely what astronomers witnessed in the late 1990s when they studied distant supernova, expecting to see the universe's expansion slowing under gravity's grip. Instead, they found the opposite. Galaxies were fleeing from one another at ever-increasing speeds, as if some invisible hand were stretching the cosmos apart. This wasn't just a tweak to the equations, it was a revolution. Dark energy, a repulsive force woven into the fabric of space, had entered the story, and nothing would ever look the same. What makes dark energy so baffling isn't just its effect, it's the sheer dominance of it. Think of the universe's contents as a cosmic pie chart. Ordinary matter, the stuff of stars, planets, and us, makes up a meager 5%. Dark matter, that mysterious gravitational glue holding galaxies together, accounts for about 27%, the remaining 68%. Dark energy, it's the majority shareholder in reality, yet we have no idea what it actually is. Einstein's cosmological constant, a term he once called his greatest blunder, has resurfaced as the leading candidate, a sort of background energy inherent to empty space itself. But alternatives abound, from exotic fields that change over time to radical theories where gravity itself behaves differently on cosmic scales. Here's where the universe's shape gets tangled in the mystery. Dark energy doesn't just push galaxies apart. It warps the geometry of spacetime, flattening the cosmos over vast distances. Imagine blowing up a balloon with invisible ink. As it inflates, faint lines on its surface stretch and fade, becoming harder to trace. That's the challenge cosmologists face. The more dark energy accelerates expansion, the more it dilutes the subtle curvature clues we rely on, like the cosmic microwave background's faint wrinkles or the clustering of galaxies. It's as if the universe is actively erasing its own blueprint, making the quest to measure its shape exponentially harder with time. And then there's the ultimate question: where does this lead? If dark energy remains constant, the universe faces a cold, lonely fate, the Big Freeze, where galaxies vanish over the horizon, stars burn out, and space becomes an infinite, empty void. But if dark energy intensifies, it could trigger a big rip, shredding atoms apart in a final, violent crescendo. There's even a haunting third possibility, that dark energy might one day flip sign, becoming attractive instead of repulsive, pulling the cosmos back into a fiery collapse. Each scenario hinges on the universe's shape. A flat or hyperbolic geometry dooms us to eternal expansion, while a closed universe might still reverse course, collapsing into a singularity. The irony is profound. Dark energy, the force that makes the universe's shape so hard to measure, might also hold the key to understanding it. Future telescopes, like the Roman Space Telescope or the Square Kilometre Array, aim to map dark energy's influence with unprecedented precision, tracing how it's warped the cosmos over billions of years. And lurking in that data could be the answer we've chased for centuries, not just the shape of space, but the destiny of everything within it. The universe isn't just expanding. It's telling a story, and dark energy is the plot twist we're still learning to read. The idea of a multiverse doesn't just expand our cosmic horizons, it shatters them. Picture a frothing ocean where each bubble is an entire universe, inflating from its own Big Bang, governed by its own rules. In this sea of realities, our universe's near-perfect flatness might not be a universal law at all, just a local accident, one possible shape among infinite others. String theory takes this further, suggesting these alternate realities could have entirely different dimensions, some crumpled into tiny loops, others stretched into geometries our brains can't even visualize. A universe with 4 spatial dimensions might fold like a hypercube, while another with 7 could twist into shapes that make black holes look simple. What's wild is how close these ideas come to testable science. Inflationary cosmology, our leading theory of the universe's explosive beginning, naturally predicts a multiverse. When space expanded faster than light during inflation, quantum fluctuations could have sparked endless pocket universes, each with random properties. Most might collapse instantly or spawn laws too chaotic for life, but a rare few like ours would land on the delicate balance needed for galaxies, stars, and thinkers. It's like rolling a cosmic die an infinite number of times. Eventually, you'll get a universe where the numbers line up just right. The implications rewrite what infinity even means. If the multiverse is real, then every conceivable cosmic shape exists somewhere: spherical universes, saddle-shaped ones, even knots of spacetime so complex they defy description. Some might harbor dark energy stronger than ours, tearing themselves apart in seconds. Others could curve so tightly they're microscopic, hidden dimensions curled inside every atom. And somewhere out there, in the vastness of possibilities, another version of you might be staring at a night sky shaped entirely differently, where parallel lines converge, or triangles have 4 sides. Critics argue this is philosophy dressed as physics, untestable by definition. But hints might lurk in the cosmic microwave background's faintest anomalies, or in the way black holes evaporate, potentially leaking traces of other universes. Future gravitational wave detectors could even catch echoes from collisions between our universe and another. For now, the multiverse remains a dazzling what if, a reminder that our universe's shape might not be the rule, just one stroke in a canvas too vast to see. Now let's zoom from the cosmic scale to the most extreme warps in spacetime, black holes. These aren't just cosmic vacuum cleaners, they're laboratories for extreme geometry, where space and time twist into knots. Near a black hole's event horizon, gravity is so intense that light itself bends into circular orbits, trapped like a car on a cosmic roundabout. Step inside, and the curvature becomes infinite, a singularity where spacetime's fabric shreds entirely. It's here, in these violent distortions, that we might find clues to the universe's deepest geometric secrets. black holes aren't just cosmic vacuum cleaners, they're the ultimate expression of warped spacetime, places where gravity wins its battle with reality. Picture standing near the edge of one, staring into the abyss. The light from your feet, pulled upward by unimaginable forces, would stretch into crimson streaks before vanishing. Time itself would slow to a crawl, seconds dragging like years for anyone watching from afar. This isn't science fiction. It's the brutal geometry of Einstein's equations playing out in real time, a reminder that space isn't just curved, it can tie itself into knots. What makes black holes so extraordinary isn't just their destructive power. It's how they reveal the intimate dance between mass and geometry. The more massive the object, the deeper it dents the fabric of spacetime, like a bowling ball sinking into a trampoline. But black holes take this to the extreme. Their gravity is so intense that near the event horizon, the point of no return space bends back on itself like a twisted ribbon. Light, which normally travels in straight lines, gets forced into circular orbits, trapped in an endless loop just outside the black hole's grasp. These photon spheres are cosmic hallways of mirrors, where a single beam of light could, in theory, orbit forever if not for the slight tug of quantum fluctuations. This extreme curvature isn't just a spectacle, it's a laboratory. By studying how black holes bend light and slow time, physicists can test the limits of general relativity and probe questions about the universe's larger shape. Some theorists have even proposed a mind-bending idea. What if our entire cosmos is the interior of a higher dimensional black hole? In this scenario, the Big Bang wasn't the beginning of everything. It was the moment our universe formed inside the collapsed core of some colossal, four-dimensional star. It's a wild thought, but it's not pure fantasy. The equations hint at eerie parallels between the singularity at a black hole's heart and the infinite density of the early universe. Both represent points where spacetime's curvature becomes so extreme that our current physics breaks down, screaming for a deeper theory to take over. That's where quantum mechanics enters the story. At the smallest scales, the smooth geometry of general relativity gives way to a frothing, probabilistic foam where space and time fluctuate wildly. Near a black hole's singularity, these quantum effects could prevent the infinite curvature predicted by classical physics, replacing it with something stranger, a bounce, a bridge to another universe, or a knot of spacetime so tangled it defies description. Some models suggest that black holes might not be eternal prisons at all, but tunnels to other regions of spacetime, hidden behind veils of quantum uncertainty. The implications ripple outward. If black holes can warp space this severely, what does that say about the universe's overall shape? Could the same quantum effects that smooth out a singularity also subtly curve the cosmos on the largest scales? It's a puzzle that ties the infinitesimally small to the unimaginably vast, reminding us that the fabric of reality might be more interconnected than we ever dreamed. As we peer deeper into these mysteries, we're not just studying black holes, we're using them as lenses to glimpse the universe's hidden geometry. Every gravitational wave they emit, every distortion they imprint on passing starlight, carries clues about how spacetime bends, twists, and ultimately shapes the story of everything. And somewhere in that interplay between the infinitely dense and the endlessly vast, we might just find the answer to the ultimate question: what shape is our universe really? If spacetime were a tapestry, then at the smallest scales imaginable, far smaller than an atom, smaller even than a proton, the threads of that tapestry would fray into a seething, chaotic whirlpool. This is the quantum foam, a frothing ocean where reality itself loses its smooth certainty and becomes a probabilistic storm. At the Planck length, a distance so tiny that a human hair is wider by comparison than our entire solar system, space and time cease to behave as we know them. Instead, they churn with fleeting wormholes, virtual particles blinking in and out of existence, and bubbles of spacetime that twist and dissolve like foam on a wave. It's a realm where the very concepts of here and now break down, replaced by a turbulent dance of uncertainty. This isn't just microscopic weirdness. The quantum foam might hold the key to understanding the universe's largest structures. Imagine walking on what looks like a perfectly flat beach, only to realize the sand beneath your feet is made of countless tiny, shifting grains. That's the cosmic illusion. We might be living in a universe that appears smooth and flat on large scales, but whose foundations are a roiling quantum sea. Some theories suggest these Planck-scale fluctuations could have left echoes in the cosmic microwave background, subtle imprints that inflation later stretched across the entire sky. Others propose that wormholes in the quantum foam might thread through spacetime like hidden stitches, connecting distant regions of the cosmos in ways we can't yet detect. String theory adds another layer of mystery. If the universe has extra dimensions, tiny, curled-up shapes hidden at every point in space, they could be tangled in the quantum foam's chaos. Picture a garden hose lying on the ground. From a distance, it looks like a simple line, but up close, you see it's a cylinder. Similarly, what we perceive as empty space might be teeming with microscopic, folded dimensions, their geometry fluctuating wildly in the foam. This could explain why our universe appears so flat. Those extra dimensions might average out the foam's turbulence, smoothing spacetime into the vast, seemingly uniform expanse we observe. Yet the quantum foam isn't just a theoretical playground, it's a battleground for physics itself. Here, Einstein's relativity, which describes gravity as the curvature of spacetime, collides with quantum mechanics, where particles defy certainty and exist in probabilities. Reconciling these two frameworks is the holy grail of modern physics, and the foam is where they meet most violently. Some models suggest that spacetime itself might be pixelated at this scale, like a digital image made of indivisible atoms of reality. Others propose that the foam's wormholes could be the seeds of black holes or even entire universes, bubbling up from the quantum depths, the wildest implication. If the foam's turbulence connects to cosmic inflation, the universe's explosive early growth, it could mean our entire cosmos is just one bubble in an endless quantum froth. Inflation might have smoothed our local patch of spacetime, ironing out the foam's wrinkles to create the flat, uniform universe we see today. But beyond our cosmic horizon, other bubbles might exist, each with different geometries, different physics, even different numbers of dimensions. It's a humbling thought. The universe's vast, majestic structure might owe its shape to the frenetic jittering of spacetime at the very smallest scales. As we peer deeper into this quantum frontier, we're not just studying tiny fluctuations, we're tracing the origins of space itself. Every experiment probing the Planck scale, from particle colliders to gravitational wave detectors, brings us closer to understanding how the foam's chaos gives rise to the cosmos's order. The answers won't just rewrite physics textbooks, they'll reveal whether the universe's geometry is written in the foam's fleeting bubbles, hidden in dimensions too small to see, or woven into something stranger still. In the first sliver of a second after the Big Bang, the universe did something extraordinary. It didn't just expand, it exploded outward faster than light itself. This was inflation, a cosmic growth spurt so violent that it stretched space a trillion times over in less time than it takes light to cross a single atom. Picture an ant standing on a deflated balloon, then suddenly, the balloon inflates to the size of Earth. That ant's world just became unimaginably vast and smooth. That's what inflation did to spacetime. It took any primordial wrinkles, any unevenness left over from creation, and ironed them out into the near-perfect flatness we observe today. But inflation wasn't just a cosmic steamroller, it was a sculptor. Those tiny quantum fluctuations, the microscopic jitters in the fabric of reality, got stretched along with everything else. What started as subatomic shivers became the seeds of galaxies, the blueprints for everything we see. The same force that flattened the universe also planted the structures that would grow into the cosmic web we inhabit. It's a paradox. The very process that erased the universe's curvature on large scales also wrote the instructions for its complexity, the wildest part. Inflation might still be happening. Some theories suggest our universe is just one bubble in an endless froth of inflating space, where new universes constantly bud off from quantum foam like bubbles in a boiling pot. In this eternal inflation scenario, infinity isn't just a concept, it's a factory, endlessly producing universes with different shapes, different laws, even different numbers of dimensions. Our flat, balanced cosmos could be a statistical fluke, a rare bubble where the numbers lined up just right for stars, planets, and life. Yet for all its explanatory power, inflation leaves gaping questions. Why did it start? What stopped it? The leading theories point to a hypothetical field called the inflaton, whose energy drove the exponential expansion. But like dark energy, the inflaton remains purely theoretical, a placeholder in our equations. Some models suggest inflation ended when this field collapsed, releasing its energy as the hot soup of particles we call the Big Bang. Others propose more exotic endings, where inflation cessation created not just our universe, but a cascade of others, each with its own geometry. The search for answers isn't just philosophical, it's etched into the sky. Inflation's violent expansion should have sent shockwaves through spacetime itself, generating gravitational waves that still ripple through the cosmos today. These waves, if detected, would carry fingerprints of inflation's energy scale, offering clues about whether it truly was a one-time event or part of an eternal cycle. Experiments like the upcoming Light-Bird satellite aim to hunt for these primordial ripples in the cosmic microwave background, while ground-based detectors listen for their faint echoes. What's at stake isn't just the history of our universe, it's the nature of reality itself. If inflation is eternal, then the cosmos isn't just vast, it's inexhaustible, a fractal of universes where every possible shape and law plays out somewhere. But if inflation was a singular event, a unique spark in the void, then our universe's flatness becomes even more mysterious, a cosmic coincidence begging for deeper explanation. Either way, the answer won't just tell us about the past. It will redefine what's possible in the endless expanse we call home. Gravitational waves aren't just cosmic messengers. They're echoes of spacetime itself, rippling outward from the most violent events in the universe. When LIGO first detected these waves in 2015, the signal came from two black holes spiraling into each other over 1 billion light-years away. But what the headlines didn't capture was the deeper revelation. Those waves carried fingerprints of the universe's geometry. As they traveled through the cosmos, their shape and timing could have been subtly altered by the curvature of space itself. A closed universe might bend their paths like sound waves echoing in a cathedral, while an infinite, flat cosmos would let them race onward undisturbed. This isn't just about black holes. Neutron star collisions detected in 2017 sent gravitational waves rippling through space alongside flashes of light, a cosmic multitool for measuring the universe's shape. By comparing the arrival times of these signals, scientists could test whether spacetime is warped on colossal scales. But the real prize lies in the future. Upcoming observatories like LISA, a space-based gravitational wave detector, could catch whispers from the universe's first moments, primordial waves from inflation itself. These would be the ultimate time capsule, carrying imprints of spacetime's geometry when it was just a trillionth of a second old. Some theories suggest a tantalizing possibility. If the universe is closed, gravitational waves might loop around it like ripples in a spherical pond, creating faint echoes that arrive years or even centuries after the original signal. It's a ghostly idea, a proof that we're living inside a cosmic hall of mirrors, where even spacetime's vibrations can't escape. Other models propose that certain gravitational wave frequencies could resonate with hidden dimensions, revealing geometries beyond our three-dimensional perception. But here's the twist. Gravitational waves don't just reveal the universe's shape, they challenge our notions of where it begins and ends. If space is finite but unbounded, like the surface of a balloon, then asking where the center lies becomes meaningless. There's no middle to a sphere's surface, just as there might be no center to the cosmos. Yet our instincts rebel against this. We're wired to think in terms of edges and centers, of a universe that unfolds from some definitive starting point. The truth might be far stranger, a reality where every point is equally central, and the very idea of an edge is a cosmic illusion. This brings us to one of cosmology's oldest questions. Does the universe have a center, or are we all just floating in an endless, edgeless expanse? The answer could rewrite not just our maps of the cosmos, but our place within it. The idea of a cosmic center feels natural after all. Everything in our daily experience has a middle point. But the universe plays by different rules. Picture blowing up a balloon covered in tiny dots. As it inflates, every dot moves away from every other dot, yet no single point on that surface is truly the center of the expansion. That's the paradox of the Big Bang. It didn't explode outward from a specific location. It happened everywhere at once, stretching space itself like that balloon's surface. Look out at the night sky, and you're seeing galaxies racing away in all directions, not because we're at some privileged midpoint, but because the fabric between them is stretching, carrying them apart like raisins in rising bread dough. This leads to something even stranger. If the universe is finite but unbounded like the surface of a sphere, then the very concept of an edge becomes meaningless. Sailors once feared falling off the Earth's edge, only to discover they were traveling a globe with no boundaries. The cosmos could be the same, just in higher dimensions. A traveler setting off in one direction might eventually loop back to their starting point without ever hitting a wall or a void. The difference is scale. Earth's surface is tiny enough to circumnavigate, while the universe's curvature, if it exists, would be so vast we'd never perceive the bend. Yet infinity complicates things further. If space truly has no end, then boundaries become a trick of perspective. Even in an infinite cosmos, any observer would see galaxies receding evenly in all directions, creating the illusion of being at the center. It's like standing in an endless forest. No matter where you are, your view looks the same in every direction, giving the false impression you're at its heart. This cosmic democracy is baked into the math. No location is special, and no vantage point reveals the true structure of the whole. Now, take this a step further with the holographic principle, one of the most radical ideas in physics. It suggests that our three-dimensional universe might be a projection of information encoded on a two-dimensional surface at its boundary, like a movie screen rendering a three-dimensional world. If true, the universe wouldn't need edges in the traditional sense. Instead, all the information about everything, every star, every atom, even your thoughts, could be stored on this distant, invisible surface. It's as if the cosmos is a cosmic Instagram post, with our rich 3D reality being merely the filtered version of a deeper, flatter truth. The holographic principle turns intuition inside out. Suddenly, black holes, those ultimate destroyers, become key players. Their event horizons, it turns out, might act like those two-dimensional surfaces, encoding information about what falls inside in pixel-like bits. This isn't just philosophy. Experiments with quantum gravity and string theory suggest that the mathematics of a higher dimensional universe can perfectly match the math of a lower dimensional boundary. It's as if the universe is playing a shell game, hiding its true shape in plain sight. So where does that leave the idea of edges and centers? In a holographic cosmos, the very question might be a misdirection. The boundary isn't out there in space. It's a shadow realm, a hidden layer where the universe's blueprints are stored. And if infinity has edges, they're not walls or cliffs. They're more like the edges of a painting, framing a reality that's both deeper and stranger than we ever imagined. The night sky isn't just a window to the universe's shape, it's a mirror, reflecting back questions we're only beginning to ask. What if everything you see, touch, and experience, every star, every atom, even the screen you're staring at right now, is nothing more than a grand illusion? The holographic principle dares to suggest exactly that. Picture a concert hall where a flawless 3D projection springs from a flat, two-dimensional screen. Now scale that up to cosmic proportions. This radical theory proposes our universe operates the same way, a three-dimensional reality that's actually encoded on a distant, two-dimensional surface, like a cosmic barcode storing the blueprints for everything. It's not science fiction, it's a serious hypothesis born from the math of black holes and string theory, one that could rewrite our understanding of space, shape, and even existence itself. The idea first gained traction when physicists studying black holes stumbled upon a paradox. These cosmic vacuum cleaners don't just swallow matter, they erase information, which quantum mechanics insists should never disappear. The solution: black holes might encode everything they consume on their event horizons, the spherical surfaces marking their points of no return. Just as a DVD stores a movie's data in flat, microscopic pits, an event horizon could store a star's worth of information across its two-dimensional surface. Take this logic further, and suddenly, the entire universe might function the same way, with every particle, every force, every flicker of light being nothing more than a hologram projected from some unseen boundary. This flips conventional geometry on its head. Instead of spacetime having inherent shape, flat, spherical, or hyperbolic, its structure could emerge from deeper, simpler rules playing out in lower dimensions. Think of how the intricate patterns in a kaleidoscope emerge from the reflection of a few colored beads. Similarly, the universe's apparent three-dimensional richness might arise from interactions we can't yet perceive. Some models even suggest that gravity, the force that sculpts cosmic structure, isn't fundamental at all, but a side effect of this holographic encoding, like the way temperature emerges from the motion of atoms. Evidence for this wild idea is scarce but tantalizing. Physicists have found mathematical equivalences between theories describing three-dimensional universes and those describing two-dimensional boundaries, like discovering that a novel and its movie adaptation, despite different formats, tell the same story. Experiments with quantum entanglement, where particles mirror each other's states instantaneously across vast distances, hint at hidden connections that could reflect a deeper, lower-dimensional reality. Even the cosmic microwave background's patterns show anomalies that some researchers argue might be fingerprints of a holographic universe, like glitches in a simulated world. Yet the holographic principle raises profound questions. If reality is a projection, where is the projector? Is the boundary of our universe a physical surface or an abstract mathematical construct? And how does time, the one dimension that stubbornly resists holographic description, fit into this framework? These aren't just academic puzzles. If true, holography would mean the universe's shape isn't a fixed geometry but a dynamic illusion, a dance of information unfolding on a hidden stage. The night sky, with its galaxies and voids, would be the grandest special effect of all, a cosmic magic trick where the real action happens somewhere we can't see. For now, the holographic universe remains a hypothesis, albeit one with growing mathematical support. Future experiments like ultra-precise measurements of quantum noise or deeper probes of black hole physics might one day reveal whether we're living in a three-dimensional reality or the world's most elaborate shadow play. Either way, the theory forces us to confront a humbling possibility that the universe's true shape might not be written in the stars, but in codes we're only beginning to decipher. And that leads us to an even bigger mystery: how time, the invisible thread weaving through all of existence, fits into this cosmic tapestry. Time isn't just a ticking clock, it's the invisible thread weaving through the fabric of spacetime, pulling the universe forward in one unshakable direction. This relentless march, known as time's arrow, is etched into everything from the shattering of a wineglass to the fading glow of dying stars. But here's the twist: in Einstein's relativity, time isn't separate from space, it's the fourth dimension, intertwined with the universe's geometry like a helix spiraling through the cosmos. If space can curve, why not time? Some theories suggest that in a closed universe, time itself might loop back like a cosmic Möbius strip, where the future circles around to meet the past. Picture a world where every ending is a new beginning, and the Big Bang isn't just the start, it's the echo of a cycle repeating across eternity. Yet time's behavior isn't just about loops. Quantum mechanics throws a wrench into the works with its own radical idea: that time might not be fundamental at all. At the smallest scales, particles don't experience time as a smooth flow, but as a jumble of probabilities where cause and effect blur like ripples in a pond. Some physicists argue that what we perceive as time's arrow is actually an illusion, emerging from the quantum entanglement of particles, like a cosmic game of telephone where every interaction passes along the illusion of now. It's as if the universe is a vast, interconnected network, and time is just the way we experience the nodes lighting up one after another. This duality, time as both a geometric dimension and an emergent mirage, forces us to rethink spacetime's true shape. A closed universe with looping time would have a structure as intricate as a Klein bottle, where past and future fuse into a single, seamless surface. An open universe, though, might treat time like a one-way river, carving irreversible channels through the void. And if time is truly an illusion, then the universe's geometry could be something far stranger. A static, unchanging block where all moments exist at once, and our perception of movement is just a trick of perspective. The implications ripple across cosmology. If time loops, could evidence linger in the cosmic microwave background, ghostly echoes of previous cycles imprinted on the sky? If time is emergent, might we find cracks in the illusion, moments where quantum weirdness lets us peek behind the curtain? These aren't just thought experiments. Experiments with entangled particles and quantum gravity simulations are already testing the boundaries of time's nature, probing whether it's a fundamental force or a cosmic side effect. Now shift gears to another clue hidden in the heavens: cosmic crystallography. Just as crystals repeat their atomic patterns in 3 dimensions, could spacetime itself harbor repeating structures on a universal scale? This bold idea suggests that if the universe is finite and oddly shaped, like a donut or a dodecahedron, light might wrap around it, creating duplicate images of galaxies or ghostly echoes of the Big Bang. Imagine holding a kaleidoscope up to the night sky, where distant constellations aren't just random scatterings but reflections of a hidden geometric order. Astronomers have scoured galaxy surveys for these cosmic fingerprints, hunting for identical clusters of stars mirrored across the void. So far, the search has turned up empty, but the hunt isn't over. The beauty of cosmic crystallography lies in its simplicity. Unlike abstract theories of extra dimensions or quantum foam, it offers a direct, observational test for the universe's topology. If space loops back on itself, even subtly, the patterns should be there waiting in the data, like a faint watermark on the fabric of reality. Future telescopes, like the Vera Rubin Observatory, could finally spot these repetitions, revealing whether the cosmos is a vast, echoing hall or an infinite, untiled plane. Together, time's mysteries and crystallography's patterns remind us that the universe's shape isn't just about where we are. It's about when we are and how all those threads intertwine. The answers won't just redraw our maps of space, they'll rewrite the story of existence itself. Cosmic crystallography isn't just a tool, it's a cosmic detective story, one where the universe's shape might be revealed not by grand equations, but by subtle echoes hidden among the stars. The premise is simple yet profound. If space loops back on itself like a giant three-dimensional donut, light from distant galaxies could travel multiple paths around the cosmos, reaching us from different directions. Imagine standing in a mirrored room where every object reflects endlessly in every direction. Now scale that up to the universe. A single quasar might appear duplicated across the sky, its image wrapped around the curvature of spacetime like a cosmic hall of mirrors. Astronomers have scoured galaxy surveys for these ghostly duplicates, searching for identical clusters of stars or matching supernova that could betray the universe's hidden topology. The Sloan Digital Sky Survey, which mapped millions of galaxies, would have been the perfect place to spot these repetitions, yet so far, the sky remains stubbornly unique. No mirrored galaxies, no telltale echoes, but absence of evidence isn't evidence of absence. The universe's curvature could be so vast that light hasn't had time to complete even a single loop in 13.8 billion years. Or perhaps the repetitions are there, camouflaged by cosmic expansion, their light stretched and dimmed beyond recognition. The search isn't over. Next-generation telescopes like the Vera Rubin Observatory, with its panoramic view of the heavens, could finally catch these elusive patterns. By mapping billions of galaxies with unprecedented precision, it might spot the faint fingerprints of a closed universe, subtle correlations in the positions of distant objects that betray the cosmos's true shape. Even gravitational waves, those ripples in spacetime, could carry hints. If space loops back on itself, these waves might arrive at Earth from multiple directions, like echoes bouncing through a cosmic canyon. Now shift perspective. How would an alien civilization, perched on a planet in some distant galaxy, perceive the universe's geometry? Their vantage point might reveal patterns invisible to us, like a viewer standing in just the right spot to see the full symmetry of a kaleidoscope. For all we know, they've already mapped the universe's topology by spotting duplicates of our own Milky Way in their night sky. Or perhaps they're grappling with the same mysteries. They're astronomers staring into the void and wondering if space stretches forever or folds back in on itself. This shared cosmic quest transcends species and time. Whether human or alien, we're all stargazers trying to decipher the shape of the stage beneath our feet. And while the answer remains hidden, the search itself reshapes our understanding not just of space, but of our place within it. The universe might yet reveal its secrets in the faintest of echoes, the quietest of repetitions, waiting for the right observer to connect the dots. Imagine a civilization that evolved on a planet orbiting a star in the dense core of a globular cluster, where the night sky blazes with a million suns packed shoulder to shoulder. Or a species born in the vast emptiness between galaxy superclusters, where the nearest neighbor galaxy appears as nothing more than a faint smudge. Their cosmic perspective, their very intuition about space and geometry, would be fundamentally rewired by their environment. Where we see a universe of orderly expansion and near-flat geometry, they might perceive patterns invisible to us, subtle gravitational lensing from dark matter filaments acting like a funhouse mirror, or spacetime curvature so pronounced in their dense stellar neighborhood that parallel lines visibly converge. Their textbooks could describe a universe that looks nothing like ours, not because the cosmos changed, but because their starting point altered the very questions they thought to ask. Consider how differently they might interpret the same evidence. Our measurements of the cosmic microwave background rely on Earth's position in a relatively quiet galactic suburb. But what if their planet orbited a black hole binary where extreme gravity distorts every signal? The faint temperature variations we painstakingly map might arrive to them scrambled, forcing them to invent entirely new mathematics to decode the universe's shape. Even something as fundamental as redshift could be upended. In regions of intense gravitational potential, light loses energy climbing out, potentially mimicking the effects of cosmic expansion where none exists. Their flat universe might be an artifact of their location, just as ours could be. This isn't just speculation, it's a mirror held up to our own blind spots. Human perception is built to navigate three-dimensional space at human scales. We instinctively balk at the idea of a four-dimensional hypersphere or a hyperbolic plane because we lack the sensory apparatus to visualize them. But a species that evolved in a radically different environment might treat these concepts as intuitively as we grasp left and right. Their mathematicians might have discovered cosmic topology centuries before inventing telescopes, simply because their cultural myths were steeped in cyclical time or Mobius-like symmetries. The real test would come if we ever compared notes. Would their most advanced telescopes confirm our Wilkinson microwave anisotropy probe data, or would they point to anomalies we dismissed as noise? Perhaps they've already detected the faint imprint of a rotating universe, a subtle spiral pattern in the polarization of ancient light that our instruments aren't sensitive enough to catch. Or maybe they laugh at our flatness problem, having long since proven that what we perceive as flat is actually a local bubble in a far vaster multiverse with fractal geometry. This thought experiment reveals a humbling truth. The universe's shape isn't just a physical property, it's a dialogue between reality and the observer. Every measurement we make is filtered through layers of assumptions, technological limits, and the accident of where and when we happen to exist. The cosmos might be whispering its secrets in 1,000 different ways, but we're only hearing one dialect. Now shift from alien minds to human philosophy. If infinity feels like an abstract concept to us, how would it appear to a civilization whose very survival depended on navigating curved spacetime? Some cultures might worship it as a divine loop, others fear it as an inescapable maze, but all would share one realization. The universe's geometry isn't just a map, it's a mirror, reflecting back the limits of whoever dares to measure it. Infinity isn't just a number, it's a mirror held up to the limits of human thought. Take Zeno's paradoxes, those ancient Greek puzzles that still tie brains in knots 2,500 years later. How can an arrow ever reach its target if it first must cover half the remaining distance, then half of what's left, and so on, an endless subdivision of space and time? The paradox reveals something profound. Our intuition crumbles when faced with the infinite. We're wired to think in terms of beginnings and endings, yet infinity laughs at such neat boundaries. It's no wonder philosophers from Aristotle to Kant wrestled with whether infinity was real or just a mental crutch. a way to patch over gaps in our understanding. Fast forward to the 19th century when mathematician Georg Cantor turned infinity into a playground. He didn't just accept infinity, he catalogued it, proving there are different sizes of endlessness. The counting numbers 1, 2, 3 are infinite, but the real numbers, all decimals between 0 and 1, form a larger infinity, so vast that no list could ever contain them. This hierarchy of infinities, some countable, some uncountable, shook mathematics to its core. Cantor's work suggests that if the universe is infinite, it might not be a single, uniform expanse. There could be layers of infinity woven into spacetime itself, regions where complexity multiplies beyond all reckoning. Yet not everyone buys into infinity's physical reality. Some physicists and philosophers argue it's merely a useful abstraction, a placeholder for big enough that we can't see the end. The observable universe, after all, has firm boundaries. We can't see beyond the cosmic horizon where light hasn't had time to reach us in 13.8 billion years. Even if space stretches forever, the knowable universe is decidedly finite. This tension between the infinite ideals of mathematics and the hard edges of observation fuels endless debate. Is infinity a feature of nature or a quirk of human cognition? The implications ripple beyond equations. If the universe is truly infinite, then somewhere out there, every possible configuration of matter must exist, including exact copies of you reading this script, variations where history unfolded differently, and realities so alien they defy description. It's a dizzying thought, one that blurs the line between science and metaphysics. Conversely, if infinity is just a tool, then the cosmos might be simpler than we've dared to imagine. A vast but bounded stage where every phenomenon, no matter how extraordinary, plays out within fixed rules. These debates remind us that the universe's shape isn't just about curvature or topology. It's about meaning. Whether infinite or finite, the cosmos forces us to confront our place within it. Are we fleeting specks in an endless void, or integral threads in a grand but finite tapestry? Later, we'll revisit the observable universe's hard limits, but for now, sit with the awe that comes from staring into the infinite, knowing it stares back, asking questions we've only begun to frame. Even in an infinite cosmos, our view is stubbornly finite. A glowing sphere just 93 billion light-years wide, where every star, every galaxy, even the fading whisper of the Big Bang itself, sits trapped inside an invisible cage. This is the observable universe, the ultimate prison of perspective, built not by walls but by the speed of light itself. Imagine standing in a vast, dark forest with a lantern that only illuminates a small circle around you. No matter how endless the trees might be, your world is defined by that tiny pool of light. That's our predicament. Galaxies near the edge of this cosmic bubble aren't just far away, they're vanishing. Their light stretched into invisibility as space itself carries them beyond our horizon faster than their photons can chase us. What's wild is how this limit warps our understanding of infinity. If space truly has no end, then everything we've ever seen, every quasar, every supercluster, is less than a speck of dust in an endless desert. The cosmic microwave background, that ancient glow from the universe's infancy, is just the first chapter of a story whose later pages are forever out of reach. Telescopes like Hubble and James Webb push our vision deeper, but they're up against a fundamental law. Light from beyond the horizon will never reach us, no matter how long we wait. The universe could be teeming with wonders we'll never know, civilizations blooming and dying in the darkness, their existence erased by the relentless expansion of space. Yet this horizon isn't static, it's shrinking, not because the universe is collapsing, but because dark energy is accelerating its expansion. stretching the distance between galaxies like a rubber sheet pulled taut. Over billions of years, galaxies we see today will redshift into nothingness, their light too feeble to detect. Eventually, the observable universe will contract to a lonely island of stars, the rest of creation slipping forever into the night. Future astronomers might peer into the void and see only blackness, with no clue that countless galaxies once lit the sky. Here's the twist: the shape of the universe could rewrite this grim epilogue. In a closed, spherical cosmos, gravity might eventually halt expansion, pulling everything back in a fiery reversal. Life could persist near the crash, huddled around black holes for warmth as atoms themselves dissolve. A flat or hyperbolic universe, though, dooms us to that cold fade out unless dark energy behaves unpredictably or hidden dimensions reshape the game. The fate of life isn't just about time, it's about geometry. So while we're trapped in our finite bubble, the universe's true shape holds the key to whether we're riding a one-way slide into oblivion or part of a cycle where even infinity gets a second chance. The fate of life in the cosmos isn't just written in the stars, it's etched into the very shape of spacetime. Picture a flat, ever-expanding universe where galaxies drift apart like lonely ships on an endless dark sea. Over trillions of years, stars will exhaust their fuel, black holes will evaporate, and the universe will fade into a featureless void, its temperature dropping toward absolute zero. This is the heat death, the coldest possible ending, where even time loses meaning in a sea of perfect stillness. It's a grim portrait of the far future, but it's not the only one. Now imagine a closed universe where gravity eventually halts expansion and pulls everything back in a fiery reversal. Galaxies would rush toward one another, their light blue shifting as space contracts. Temperatures would soar until atoms themselves unravel in a final, cataclysmic big crunch. For life, this scenario offers a paradoxical sliver of hope. A universe that recycles itself might also reboot the conditions for new beginnings. Some theories even suggest that a collapsing cosmos could trigger another Big Bang, birthing a fresh universe from the ashes of the old. It's a cosmic phoenix, rising and falling in an eternal cycle. Then there's the hyperbolic nightmare, the Big Rip. If dark energy grows stronger over time, it could one day overpower gravity, electromagnetism, even the nuclear forces holding atoms together. First, galaxies would be shredded, then stars, then planets, until finally, space itself would tear apart at the subatomic level. Reality would dissolve into a storm of disconnected particles, each hurled into solitary oblivion. It's the most violent of all possible endings, a universe that doesn't just fade but is actively ripped to pieces. But what if life doesn't just accept these cosmic scripts? Advanced civilizations harnessing energies beyond our comprehension might find ways to manipulate spacetime itself. Theoretical physics offers wild possibilities: wormholes to bridge collapsing regions of space, artificial baby universes created in labs, or even uploading consciousness into indestructible quantum constructs. A society that masters the geometry of spacetime could rewrite its own destiny, escaping the heat death by tunneling to a younger universe or riding the expansion like surfers on a wave of dark energy. The deeper question is why any of this matters. The universe's shape isn't just an abstract puzzle, it's the ultimate backdrop for existence. Whether we're fleeting sparks in an infinite void or participants in an eternal cycle, the answer shapes how we understand our place in the cosmos. And perhaps in the far future, it won't just be about understanding, it might be about survival. The civilizations that endure could be the ones who learn to read the curves of space-time, and then, with ingenuity and courage, bent them to their will. The shape of the universe isn't just a cosmic curiosity, it's the foundation of our existential compass. Picture standing at the edge of an infinite void, where galaxies stretch endlessly into the dark, each one a lonely island in a sea of nothingness. Now imagine the alternative, a finite cosmos curved like a hall of mirrors where every path eventually leads you home. These aren't just abstract scenarios. They're frameworks that redefine what it means to be alive, to wonder, and to search for meaning. If space is infinite, then every possible version of reality exists somewhere out there, every choice you didn't make, every life you might have lived. But if the universe is closed, looping back on itself like a cosmic Ouroboros, then our existence becomes part of a grand, repeating cycle, where beginnings and endings blur into one. This duality cuts to the heart of human questions about purpose and connection. An infinite universe can feel exhilarating in its boundlessness, offering the promise of endless discovery, but it can also amplify our solitude, leaving us to wonder if we're just a fleeting spark in an indifferent expanse. A finite cosmos, by contrast, might feel cozier, almost intimate in its limits, yet it also raises haunting questions about what lies beyond the loop. Are we alone in this self-contained reality, or is our universe just one thread in a vast, unseen tapestry? Science's pursuit of the universe's shape is in many ways a mirror held up to our deepest anxieties and hopes. The same tools that measure the cosmic microwave background or track distant supernova are also probing the existential contours of our place in existence. When astronomers debate flatness versus curvature, they're not just crunching numbers, they're wrestling with the stage upon which all human drama unfolds. Even the search for extraterrestrial life ties back to geometry. An infinite universe makes alien civilizations a statistical certainty, while a finite one could mean we're the only actors in a cosmic snow globe. So where does the evidence point? The latest data leans toward a flat or nearly flat universe, but with enough uncertainty to leave room for awe. The cosmic microwave background's whispers, the distribution of galaxies, the dance of dark energy, all hint at a cosmos balanced on a knife's edge between finite and infinite. Yet the most profound realization isn't the answer itself, but the fact that we're here to ask the question. Whether adrift in an endless ocean or cycling through a cosmic loop, our ability to map, measure, and marvel at the universe's shape is what makes us uniquely human. As we stand on the precipice of discovery, one truth remains: the universe's geometry isn't just about space, it's about story, and ours is still being written. Flat, spherical, or hyperbolic, three cosmic shapes locked in a tug of war for reality's blueprint. The flat universe model, our current frontrunner, fits the data like a glove, with the cosmic microwave background's near-perfect symmetry and galaxy surveys aligning with Euclidean geometry. Yet whispers in the data won't let us rest. That slight temperature asymmetry in the CMB, the way distant galaxy clusters seem to clump just a hair differently than predicted, these are the cosmic breadcrumbs that keep physicists awake at night. It's like staring at a masterpiece and spotting one brushstroke out of place. Is it a flaw in the canvas or a hidden signature of something deeper? The spherical universe still has its champions, drawn to its elegant closure and finite nature. Imagine space as a vast, invisible sphere. Travel far enough in one direction, and you'd loop back to where you started, like a cosmic Magellan. While most measurements push against this model, there's a provocative idea gaining traction. What if the universe is so enormous that its curvature is imperceptibly slight, like trying to detect the Earth's roundness from a single sidewalk crack? Future missions like ESA's Euclid telescope could settle this by mapping billions of galaxies with micrometer precision, hunting for distortions that might reveal space's subtle bend. Then there's the wild card, hyperbolic geometry. A saddle-shaped universe would rewrite the rules of reality, where parallel lines diverge violently and triangles bulge inward like deflated balloons. Though current observations make this unlikely, some theorists won't let it go, especially those working with string theory's extra dimensions. If hidden dimensions curl into microscopic hyperbolic shapes, their influence might manifest in ways we're only beginning to model. It's the ultimate cosmic sleight of hand, a universe that looks flat in 3 dimensions but writhes with complexity in higher ones. The real excitement lies in the next generation of tools. Gravitational wave astronomy could crack the case wide open. If spacetime loops back on itself, ripples from colliding black holes might arrive as faint echoes, their signals having traveled multiple paths around the cosmos. Meanwhile, quantum sensors are reaching sensitivities where they might detect Planck-scale fluctuations, hints of the quantum foam that could underlie cosmic geometry. We're no longer just observers of the universe's shape, we're becoming cartographers of the invisible. What's at stake isn't just a footnote in astrophysics textbooks. A flat universe suggests an infinite reality where every possibility repeats endlessly. A closed one offers the poetry of cyclical time, a cosmos that breathes in and out. And a hyperbolic universe, that's the realm of fractal wonder where complexity multiplies without limit. The answer won't just tell us where we are, it will redefine what's possible. As we stand on the threshold of these discoveries, one truth remains. The universe's shape isn't just a question for scientists. It's a mirror reflecting humanity's endless curiosity, our refusal to accept the night sky as anything less than a riddle waiting to be solved. The shape of the universe isn't just a scientific puzzle, it's a mirror reflecting humanity's deepest questions about existence itself. For centuries, we've mapped the stars, unraveled equations, and launched telescopes into the void, all to answer one deceptively simple question: what is the true geometry of reality? Yet every discovery seems to open new mysteries. The cosmic microwave background hints at flatness, but with margins of error that leave room for wonder. Dark energy stretches spacetime in ways we can't yet predict, while quantum foam churns beneath the surface of everything we see. Even our best theories, general relativity's elegant curvature, string theory's hidden dimensions, feel like fragments of a grander truth waiting to be uncovered. This pursuit transcends mere measurement. It's a story about how we make sense of our place in the cosmos. A flat, infinite universe offers a canvas of endless possibility, where every combination of matter and energy must exist somewhere in the void. A closed universe whispers of cycles, of beginnings and endings folding into one another like an Ouroboros eating its tail. And a hyperbolic cosmos, that's the realm of fractal wonder, where parallel lines explode apart and triangles defy everything we thought we knew. Each possibility reshapes not just physics, but philosophy. What does it mean to live in a universe with edges or without them? The beauty lies in how much we've learned while standing at the edge of the unknown. A century ago, Einstein rewrote gravity as the curvature of spacetime. 50 years later, we detected the Big Bang's afterglow. Today, gravitational wave astronomy lets us listen to black holes colliding, while quantum computers simulate conditions at the birth of the cosmos. Every tool we build, from the James Webb Space Telescope to underground dark matter detectors, is a lantern held up against the dark, illuminating another piece of the puzzle. Yet the universe remains coy, revealing just enough to keep us hungry for more. Perhaps that's the real lesson. The quest to map the universe's shape isn't just about finding answers, it's about learning how to ask better questions. Each generation's certainties become the next generation's stepping stones. Newton's absolute space gave way to Einstein's flexible fabric, which may yet yield to some deeper geometry we can't yet imagine. The night sky has always been humanity's greatest teacher, not because it offers easy truths, but because it reminds us how much there is left to explore. So what do you think? Is the universe a vast, flat plane stretching endlessly into the dark? A shimmering hypersphere, curved and finite? Or something stranger still, a shape that dances between dimensions, defying all our analogies? The conversation doesn't end here. Drop your thoughts below and let's keep unraveling this cosmic mystery together. And if you've enjoyed this journey to the edge of understanding, don't forget to subscribe. There are always new horizons to explore. Until next time, keep looking up. The universe is waiting.